Hi everyone. Today we are going to talk about boosting machines and we'll see how do they work. So basically there are different ways in which we can combine multiple decision trees. The first one is bagging, which is bootstrap aggregating. So in this kind of setting we combine trees trained in parallel. So for example, the same data is going to multiple trees and every tree is getting trained parallelly, and at the end we are combining their outputs by taking majority votes in case of classifications and average in case of regression sort of problems. Okay, so this is the typical setting which we have in case of random forest, right? Then boosting is another technique where we can combine outputs from multiple decision trees, but the difference is that we train trees in a subsequent manner. So what that means is that let's say I pass data to one tree, it will return some output. Let's say the output is WL1, weak learner 1. So there is this error which was outputted by first model, y minus WL1. So my second model will try to adapt to this particular error, or it will try to predict the error made by the previous tree. After the second tree, my output becomes WL1 plus WL2, while I still have error which is y minus combination of both the trees, which is WL1 plus WL2. Now the third tree will try to minimize the error made by the second tree, right, and so on. At the end we combine output, like WL1 plus WL2 plus WL3, which is nothing but we combine outputs from all that tree together, right? So the idea behind boosting machine is that we use weak learners. The reason being that weak learners are simple models, so they can learn the generic patterns, but they cannot learn a niche pattern which is available in data, right? So niche patterns are something which is very specific to a particular data point. So weak learners tend to not learn that. The basic reason is that let's say there are trees with smaller depth, so they cannot learn the niche pattern, but they are pretty good at capturing the generic patterns. So that is the reason why we choose weak learners to avoid overfitting. Okay, next we are going to talk about GBMs, or gradient boosting machines. So boosting is one of the mostly used algorithm in ML. So let's say that this is my data set which I am using. So I want to predict weight using these three data points, which are color of eyes, height and gender. So this is my objective. So in gradient boosting we need to start with some initial prediction. So in case of regression problems, as you might have guessed, the best initial prediction would be average of all. So the average of these data points comes out to be 64.67. So that becomes my initial prediction, and residuals, as you know, it's nothing but difference between actual minus predicted values. So for example, let's say this is my regression line. This is predicted value over red line, and this blue cross we are seeing, this is observed y or the actual y. So the difference of actual minus predicted, which is this height over here, is nothing but my residuals. Okay, so I can calculate residuals for all the points. For example, for first observation, 65 was the actual weight and 64.67 was the predicted weight, so my residuals become 0.33, right? Similarly I can calculate for all. Now the objective for our first tree in the sequence of multiple trees is to predict these residuals based on these three parameters again. Okay, so let's say somehow my algorithm found out that the best split happens at gender. So for both the genders, I have these residuals plotted over here. So basically all the males, they had residuals of 0.33, 5.33, 3.33. Those we have written here. Similarly for females, minus 6.67, minus 2.67 and 0.33. Okay, then I take the average. This becomes my average residuals for male, and minus 3 becomes average residuals for females. Okay, so now I can add these residuals to my output, which is nothing but mean for the base case, right? So for males, I can add 64.67 plus 2.98, which will give me 67.65. Similarly for females, I can subtract minus 3 from 64.67, which gives me 61.67, and again I can calculate residuals. But there is some problem with this approach. The problem is that if I directly add output of a weak learner, then it might lead to overfitting, right? So idea is that instead of directly adding the output of subsequent trees, we'll add some small constant over here, which is known as learning rate or shrinkage parameter. So instead of directly adding 2.98, I will take a small step suggested by that tree. Right, so it suggested me that you should add 2.98 for males. So instead of adding 2.98 directly, I will shrink the shift by this learning rate. I've taken 0.1 for example. So 64.67 plus 0.298, that will be my new prediction for males. Similarly for females, it would become 64.67 minus 0.3, right? So basically I have combined these two quantities multiplied by eta over here. Okay, now I can calculate these residuals again, which is nothing but 65 minus 64.968, 0.032, 70 minus 64.968, 5.032, and so on, right? Okay, now let's say the second tree found out the best split to be height. All the guys with greater than 5.7 feet height came here. Their residuals are 5.032 and 3.032, and for all the observations where height was less than 5.7, these are my residuals, and the average comes out to be minus 2.0195. So after second iteration, my final prediction becomes 64.67 is the base case plus learning rate times output of first tree plus learning rate time output of second tree. So for example, for first observation, 64.67 was the mean, plus 2.98 times 0.1 plus minus of 2.0195 times 0.1, which gives me 64.76. Similarly, I can calculate for all, and these are my residuals which I received. Again, residuals are nothing but difference between actual minus this predicted value over here. So in the similar fashion, I can keep on calculating residuals and build decision trees. So we can stop it in multiple ways. For example, I can stop after a particular number of iterations, or I can define that if residuals are not decreasing by a lot, then I can stop my learning, right? So for example, let's say if a new observation comes and I have only these two trees which I train. So again, the same way, 64.67, which is the base, plus learning rate times output from this tree. So this observation being female, we have to subtract weight by 3, plus because the height is greater than 5.7, so we have to increase it by 4.032 times learning rate. So my output becomes 64.77. So this is the way we can estimate any regression problem. So I have this data set over here where I have age, gender, education, and I want to estimate whether someone voted in elections or not. Okay, so like in regression, we have to come up with the initial prediction, and in case of classification problem, it comes out to be log odds, basically log of all the events by non-events. This comes out to be 0.69 for us. So we will use this 0.69 as our base case, and we can convert this 0.69 into probabilities, because ultimately we want the probabilities using this formula, which is e raised to the power log odds by 1 plus e raised to the power log odds, and it comes out to be 0.7. So these are my initial predictions. Now I can calculate the residuals in the same fashion as we did for regression. So assuming this is the actual probability 1, and these are my initial predictions, so my residual becomes 0.3 for plus 1 cases. For 0 cases, it will be 0 minus 0.7, which is nothing but minus 0.7. Okay, so now similar to regression, we need to predict these residuals by using age, gender, and education. Let's say now this is the tree I got, which is first education, then age, and these are my residuals 0.3, 0.3 minus 0.7. Then for this split 0.3 for education undergraduate, I have 0.3 and minus 0.7. Right. So in regression, we could have directly taken average of these residuals, but because in classification we are dealing with log odds, so we have to do some kind of transformation. So this is the transformation which helps us to do classification using gradient boosting. So using this transformation, let's say for third split where education was undergraduate, so this is the predictions I get. Similarly for PG, I get minus 0.158 for age less than 35, and greater than 35 I get 1.42. So now I can directly add these to my log odds. So previously my log odds were 0.69 plus I have taken 0.5 as the learning rate over here just to show, right? And I will add output of this tree, right? So these are the things which I have gotten as new log odds. So basically we are predicting log odds and then converting them into probabilities. So using log odds, I can calculate these probabilities by using same formula, e raised to the power log odds divided by 1 plus e raised to the power log odds, right? Now I can again calculate residuals by taking this as my actual probability, which is 1 minus 0.65, it will come 0.35 and so on, right? So I can build subsequent trees and try to bring down this error. So classification works in the similar fashion as we did for regression. The only thing which we need to keep in mind is that transformation that we talked about, right? So this is about gradient boosting machine intuition in general. Next we'll see the mathematics behind it. Thanks for going through this tutorial.